Part 2 of the binary search tree tutorial. In this video, in this implementation in Java, I'm not going to include the delete node method. If you guys want me to include that, just comment on the comment section below, and I will make a separate video for that. Okay, so it's a little complicated, but let's just get started here. Let's create a new Java project. Let's call it BST, and let's create a new class, and just call it BST as well. I know it's not good practice, but hey, whatever. So just comment here, no delete node method. But I will implement the findNode method. Okay. So if you guys remember the drawing that we had earlier, it was something like this. I'm not going to draw the entire tree, just one node. Okay, it was A. Let's just say this was a value of 10. Oh, I should have put 10 instead of A. But anyway, this is a node, okay? And you had its left child and its right child going out, right? It was, wow, sorry, it's a little messy. I'm doing this on a trackpad, right? So this 10 conventionally is called a key, okay? It's the key of this node A here. And left child, right child, and everything on the left must be less than, and everything on the right of the child on the root must be greater than. This is a root node. Okay, so let's create a node class. So we have public class node. Oh, can't type today. Okay, and what we're gonna have is a key, right? This time it's gonna be an integer, and we need the left child and the right child. So we have node left child and node right child, right? Okay, let's create a constructor here for this node class, and we're gonna pass in the key, and we're just gonna simply set this key equal to the key above. And we're also gonna want to have a toString method to print out when I do the traversals. You want to be able to see the different types of traversals that's going on. So we're going to have a toString method. Okay, and we're just going to return an empty string concatenated with a key, because key is a type node, and toString is expecting to return a string. But if you concatenate, it's going to trick the method to thinking it's a string. So let's just do that. Then so far we just created we have a class called node. We don't have anything else. So now we want to define a method to add nodes to a tree, right? So I want to create this node root here outside of the add node method, so we don't lose reference to it. And we go public void add node, and we're going to pass in a key. Okay. Now, when you have this method, you don't have any nodes to add, so we have to create a node to add. So we're going to create a node called new node, and we're just going to call it instantiate that, passing the key along. Oops, what was that? Okay. Then what we want to do is, when we're adding nodes, you want to check if the root is empty, right? And if that's the case, you make the new node as a root node, and we're done. Right, so if excuse me, if root is null, we simply make root equal to new node. Okay, and if that's not the case, then we create two new nodes, namely parent, and we have a node. I keep doing that. We have a node. Let's just call it check node. I will explain what this means in a short while. I'm going to make that equal to root. Alright, so now you want to, if you get to this part of the code, that means the tree is not empty. So we're adding nodes, so we want to remember, when you add a node, if it's less than the root key value, we got to add it to the left. If it's greater than the key value of the root, you have to add it to the right. So let's create a while loop to iterate. Okay, and while true, we're going to make parent equal to check node. All right, and I will explain, like it once, as I said, what these two mean. Okay, And then we want to check if the key is less than that check node, okay? And then we do the body of that if statement. So if check node, if key that we passed is less than the check node, the key, then what we do is we move the check node. So we know it's less than, so it has to be on the left hand side. We have to add the node on the left hand side. So we make the check node point to the left side of the root. Okay, so we do check node equals check node that left child. All right, and if that left child is empty, there's nothing in that spot, which we would expect, then we make parent, not the check node, left child equal to the new node that we created above. All right, so let me explain what this means right here. Okay, oops, I misspelled that. So the reason why you don't do, and then you just I forgot to return after that. So and after that we just return, and we're done with the left side of the adding the node. So the reason why you don't do something like check node equals check node the left child equals new node is because what I'm doing here is essentially, oops, if I can spell that. Okay, so essentially what's going on here is I'm making the check node point to the root node as well as, and then the parent up here is pointing to the check node. Okay, and then what's going on here is that if the key is less than the check node, so whatever we pass, so the check node is pointing to the root. So let's say I pass in 5 and then the key is of A is 10. If the 5 is less than the check node, which is the root node key, you move the pointer of the check node to the left child here, and it will be empty, right, in this case. And then when that's null, this if statement gets executed here. And then the reason why you choose parent or left child is because now the check node is pointing to a null spot. There's nothing here, so you lose the reference to the root. So that's why you do the parent or left child. Even the IDE will tell you here that this can only be a null value here. So that's why you do the parent. That's why you need two nodes here, parent and the check node. Okay. And then similarly, if the key is not less than the check node, then you just simply do the right side checking. So else you come over here, check node. We know that it's greater than, so then you move the check node to the right child of the root. So check node equals check node the right child. All right, and you do the same conditional if statement. If check node is null, okay, you do parent the right child equals new node, and then just return, and then we're done. We're done with the adding the nodes. Okay, this is the add node method. It's very simple. All right. So then we want to implement the traversals that we talked about in part 1. Okay, so let's see what this ends. Yep. So now we want to implement the traversals. Implementing traversals is really straightforward if you understand the recursion. Okay, because it employs recursion, and it looks like when you first look at it, if it's the first time you're looking at it, it's like, this is magic, how can this work? But it does, and if you understand recursion, you will know that this absolutely works. So let's create the in order traversal first. So we go public void in order traversal, and we're gonna pass in a node, which is called this focus node. Now let's just check if this focus node is empty. As long as it's not empty, we can execute the in order traversal. Now remember, in order traversal, you visit the left side first, then the parent, and then the right side. And literally it's just 3 lines of code here. So all you do is recursively call the function, in order method, in order traversal method, traversal, and then you're just gonna enter focus node as a parameter, focus node dot left child. Okay, and then what's going on here? Oh, capital. And then to take care of the printing the parent node, the next step, we did the left side, and then you got to do the parent. We're just gonna simply print it out. That's literally all you do. Print out the focus node. And keep doing that. And then you take care of the right side. So recursively call the method. So in order traversal, and then you do focus node the right child. How simple and easy is that? Okay, so now you do same thing for post order and pre-order. So you do public void, let's do pre-order traversal. It doesn't really matter which one you do first. And we're going to pass in a node. We're also going to call this a focus node. All right, and same thing is to make sure it's not empty, as long as it's not null. So focus is not equal null. We're going to recursively call. Remember, pre-order is first visiting the parent, which is in this case a print statement, a simple print statement, and then the left side and the right side. Okay, the left and right order doesn't change. So let's print out the right, the parent first, focus node. And this print statement, we will invoke the toString method that we did here, okay, automatically. So that's why you don't need anything special, because we already took care of that toString method. And then you do recursively call the pre-order traversal method, pre-order traversal, and you just do focus node the left child, okay, and then pre-order traversal, and you're going to pass in focus node the right child, and done. How easy. Okay, beautiful and easy. And for the post order, I'm just gonna copy this. I should have done this in the beginning, make my life easier. I'm just gonna change the name. Okay, post order, and then same thing here. And the other thing that changes is we move the print statement here after the left and right traversals are done. Let's save. And let's just go through in order. So you have left child and the parent and the right child. Pre-order, you have the parent first, left, right, and then post order the parent comes after the left and right. All right, and finally, as mentioned above, we are also going to implement the findNode method. Okay, so finally we have public node, because we're finding a node, we're going to return a node. findNode. We're going to pass in the key. This is what we're looking for. Okay, a key. Okay, now I'm going to create a node called check node, and I'm going to make that equal to root, the same as above. Okay, and then we're going to create a while loop here to check with a conditional to as long as to go through the tree as long as the key of the root is not the same. Okay, so while the check node, the key does not equal key. Okay, so as long as the key that you're passing is not the same as the root, okay, we're gonna traverse the tree. So first we're gonna do the left side. So if key is less than check node the left child, okay, we're gonna move the pointer to point to the left child. Okay, so check node equals check node dot left child. Done. Else, why are you complaining here? Oh wow. Okay. Wow. Less than key. Look at that. A rookie mistake. All right. So else, we gotta make the check node point to the right child. Okay, because we know it's greater. Check node equals check node the right child. And we also want to check that if the check node is null, we want to take care of this condition as well. So if check node is null, we're simply going to return null. Okay, we didn't find a node. And then finally, we're going to return check node. And we know that if we get to here, we know that we found a node. Okay. And initially, if this while conditional statement doesn't hold, we know that the root is the one we're looking for. Alright, so then we'll be done with this. So now we have the add method and all the traversal methods already implemented along with the findNode method. The only thing that's left to do now is to actually create the tree. Now we're going to do that in the main method, public static void main. I'm going to pass the usual arguments, string array public. Okay, and then we're just going to create a new instance of this class. Alright, and we're just going to add some nodes. So add node, let's do 50. Oops. Okay, and we're going to do, I don't know, let's do 600. What was that? BST, add node, 600. Let's do a few more here. The add node, let's do 100. And here's the add node. I don't know, it's a big number, 7,000. BST, the add node, and let's just do 10. Alright, let's save. So now we have our tree here. Okay, and let's try to reconstruct the tree over here. Okay, let's get rid of that and see what we can do. So we have how many nodes that we add? 1, 2, 3, 4, 5. Okay, so we have a first node that we added is 50, so it's going to be here. This is going to be a pain on the trackpad, I apologize. Then we add 600. So remember, when we're adding, we're comparing if the key value is greater than or less than the key value of the root. So we're adding 600. So is 600 less than 550? Certainly not. So we add it to as a right child. So this is going to be 600. Okay. Ooh, that's a big number. Okay, let's add in next. This is a graphical representation of what we're doing here. Then we're adding 100. All right, 100 is certainly greater than 50, so we come to the right child, and we repeat the same process. Is 100 less than 600? That's certainly the right, so we add 100 here. It's going to be its left child, because everything to the left of it must be less than the parent. In this case, the parent is 600. Okay, then we add the next one, which is 7,000. So which is greater than 50, and then it's also greater than 600. So that's going to come over here. This is painful. This is painful. All right, I apologize. All right, and then finally we add 10, and 10 is less than 50, so it's going to be its left child right over here. All right, okay, and let's do the traversals. So what we do is let's specify which traversal we're doing, because it could be confusing. So let's print out. Let's do a simple print out statement here, and let's do in order traversal first. Okay, and we're just going to call the in order traversal on BST, and we're going to pass in the root node. Okay, so BST root. Let's print out a separate line here. System.out line, and then we're going to do let's do pre-order. So let's do system.out pre-order traversal. Alright, so we do BST pre-order, pass in that root node, and print out that blank statement so it separates it nicely. Alright, and finally we're going to do post order traversal. Why didn't I just copy and paste? Why do I keep typing everything out when I don't have to? So BST that post order and pass in that root node, and we don't need the new line here. All right, and then we'll do the find node after these traversals, okay, complete, because I want to explain how it works when you're trying to find a node. All right, so before we execute this program here, first let's save, and then now we're going to come over here and I'm going to draw out the expected values before I run this program of what to expect before it's run. So we're going to do in order first, in order. Wow, this is horrible. This is absolutely horrible. In order. So what does in order tell us? We have to visit the left side first, and then the parent, and then the right side. Okay, so we start at root node, we go to its left child, so then the 10 will be printed out. Okay, then we visit its parent, so then 50 will be printed out. Okay, and then we go to its right side, and this is a subtree, right subtree, so we apply the same thing. We visit its left side, so which is going to be 100. Okay, and then we visit the parent, which is going to be 600. This is what I expect as the output, and then finally the right side, which is going to be 7,000. Okay. Now what's next? We have pre-order. Let me try to switch colors here. It's getting a little crazy. All right, so we have pre-order. Oh my God, pre-order. Okay, so pre-order says you visit the parent first, then the left, and then the right. So we expect 50 to be printed out first because we visit that. Okay, then the left child, which is 10. Alright, and then you go over to the right child. In this case, it's a right subtree, so you apply the same thing over again. So you visit the parent first, which is 600. Okay, 600. And then you visit the left child, which is right here, the 100. That's the left child of 600, because 600 is the parent of left and right child, which is 107,000. And then you visit the right side, which is right child, and that's going to be 7,000. That's pre-order. All right, and finally we have a post order. Let's just put this here. Okay, this is post order traversal. But I'm not going to write that. Okay, post order means you do the left and right, then the parent last. Okay, so you go to the root node, you don't print it out, you visit its left child, which is 10. Okay, this is a 10. Then you go to the right side, which is a right subtree, so you have to do the same thing. You visit its left child first. In this case, it's going to be 100. All right, 100. Then you visit its right child of the parent, which is 600, and the right child is 7,000. So with post order, you do left, right, and then parent. I'll write that up top after I do this. Okay. So now the children are visited. Then you go back up to the parent because you do the parent last, and then 600 is going to be visited as a parent, and then you go back to where the root node that you came from, and then that's the parent of these two children right here, and that's going to be outputted last, which is going to be 50. Okay. Now if you're confused, just rewind this video and just watch over again. Just remember, just notice the different types of outputs of this traversal. So this is the post order is left, right, and parent. Okay. The pre-order is parent, left side, and then the right side, and the in order is the left, then the parent node. Oh, this is so horrible. And then the right side. Okay, this is what I expect the output to be. So if we save and run, let me make the console slightly bigger so you can see it. If we run this, we have in order traversals. Let's compare. So we have 10, 50, 100, 600, 1000. So we have 10, 50, 100, 600, 7000, not 1000. Pre-order traversal, we have 50, 100, 600, 100, 7000. Oops, I missed the 0 here. Okay, so 50, 100, 600, 100, and 7000. So 50, 10, 600, 100, and 7000. And with that matches. And then post order we have 100. I keep saying 100 for 10. We have 10, 100, 7,650. So we have 10, 100, 7,650. So that worked out beautifully. I didn't look like a retard. And now what we're gonna do is, let's comment this out because we don't need this junk anymore. And we're going to do something like this, and I will explain why I did the way I did it. So it's gonna be BST the findNode, and let's say we're looking for 100. Okay, and let's do if key equals null. We're going to print out key is not found. Alright, and else we're going to do system out key found. Alright, so now why I did it like this, what I'm doing here is I'm making a node, okay, a key named key, point to a node that this is going to search for. So if the 100 exists, which in this case it does, the key node is going to point at that, okay? And if the node, let's say the value we're looking for was 12, which is not in this tree, if that was the case, it would not be in the tree, and then the key node will hold a null value. So that's what I'm doing like this, and then I'm checking the if statement if the key is null. If that's the case, we know that the key doesn't exist. So if you put this as 100, right, we would expect it to be found because we have it in the tree. So if we run this program, there is found, key found. If we change that to 12, all right, it should say key not found. Beautiful. So now I'm going to explain how the findNode works. Okay, so let's go back up to its algorithm, and we're gonna make this into 2 screens. Hopefully you can still see it. Come on, get in there. Not available. Okay, that sucks. How do we do that? How do we get out of that? Anyhow, whatever. Let's try it like this. Let's try. Nope, it doesn't want to do it. Okay. Weird. But okay, anyway, so findNode algorithm. We're gonna have to resort to this. So we're creating a check node called root, and excuse me. And we have a node called check node, and we're making that point to root. So we have a check node here, okay, pointing at the root. This is a check node. All right, that's good enough. All right, then as long as the key that we're passing does not equal the root key, all right, we go through. So we compare the key, and if it's less than, in this case we have 100, right? That's the value. What was it? Yeah, 100. So it goes through, is 50 less than 100? No. So we go to the else. Okay, so then the check node here, this is pointing to now the 600 node. All right, and then you go back up to the while statement. Does it equal? No. So this condition still holds, and then you compare. You take that check node value because we have it. We moved the pointer to the right child, right? So it's pointing at the 600 value, the root's right child, and then the value is not the key, right? So you go back up to the else statement, and then you compare the 100 to 600, right? If you start, the comparison starts all over again, and 100 is certainly less than 600, So you go now the check node will point to this node, right? 600's left child. And then you go back to the condition statement, which is this is going to be false now because the key does equal the key that the check node is pointing at, and we just return the check node, which is 100. And that's how the algorithm runs. All right, and that's it for the part 2. If you enjoyed this video, please subscribe and leave a comment. Thank you for